So, welcome to this podcast on the Laplacian operator in vector calculus. And the podcast is made up of 3 exercises for you to solve, and the answers are included at the end, but I very strongly encourage you to try the questions before you look at the solutions. So, I hope that this will give you some feedback on your mastery of this material, as well as a good practice opportunity. So the first problem is to apply the Laplacian to 1 over r to the power of n, where r is the modulus of the position vector, and I'm suggesting that you do this in 3 dimensions because the answer depends on the dimensionality of the space. The second question is to show that if you apply the Laplacian to the sign of the scalar product of k dot r, that you obtain minus k squared, where k is the modulus of the vector k, which I'm assuming is just a constant vector, times the sign of the scalar product of k and r. And then finally, I'm suggesting that you try to prove this identity, that if you apply the Laplacian to the product of 2 scalar fields u and v, this can be rewritten in this way. So I suggest you write these problems down with paper and pencil and try to solve them, and then pause the video and come back to it after you have given the questions a good attempt. Okay, welcome back. Let's look at the answer to this question here. So, on this slide, I've written out the answer to the first question, and I'm just going to talk you through it. So we want to calculate the Laplacian applied to r to the minus n, where r is the modulus of the position vector r, and that means that r is the square root of x squared plus y squared plus z squared. This, as I say, is working in 3 dimensions. And the first thing to notice is that because this only depends on r, and r has this form, it means that r is symmetric under interchanging, say, x and y, or y and z, or x and z. So what I'm going to do is to calculate this term here, the second derivative with respect to x of r to the minus n, and then by symmetry we can just write down what the second derivative with respect to y is and what the second derivative with respect to z is, and the sum of these 3 terms, this plus this plus this, is the Laplacian applied to r to the minus n in 3 dimensions. So let's start calculating this second derivative. So the second derivative is the derivative of a derivative, and when we differentiate this, we're going to bring minus n in front, and that's just a constant, so I'm going to pull it outside of this derivative here, write it here. And then we reduce the power by 1, so we go from r to the power of minus n to the power of r to the minus n minus 1, which I've written here. And then, using the chain rule, we multiply by the derivative with respect to x of r. And we know what r is here, so we just rewrite this line again, minus n, derivative with respect to x, r to the minus n minus 1, and then we multiply by this. So again, we pull the half in front, we reduce the power from a half to a half minus 1, so minus a half, 1 over this square root, and then we multiply again using the chain rule by the derivative with respect to x of the argument of the brackets, and that's x squared plus y squared plus z squared, so the derivative with respect to x is 2x plus 0 plus 0. So we have a 2x factor here. And we see here now that the 2 and the half cancel, and what we are left with on the next line is minus n, derivative with respect to x, r to the minus n minus 1, but we are dividing by this, and this is r. If you just look back at the definition of r, so we have r to the minus n minus 1 divided by r, and that is r to the minus n minus 2, and then there is a factor of x. So we've calculated the first derivative, we now calculate the next derivative. So minus n is sitting there multiplying everything, and if we differentiate this first, then we're just going to be left with minus n times r to the minus n minus 2, because that derivative will be 1. And then we have the derivative with respect to x of r to the minus n minus 2, but if you think about it, we've just calculated that derivative for r to the minus n, so all we've got to do is take the result we've just obtained and rewrite n as n plus 2, because it's minus brackets n plus 2. Either that or you just do it. Whichever way, what you will obtain when you differentiate this is you're going to get another minus sign, so it's going to become plus. I'm leaving this x here because we're differentiating this. We're going to get a factor of n plus 2, just as before we had a factor of n. There's going to be another factor of x, and the power of r is going to decrease to minus n minus 4. So now, bearing in mind what these negative powers mean, we see we can rewrite this as the first term is minus n over r to the n plus 2, and the second term is n times n plus 2 times x squared, because there are two powers of x, and divided by r to the n plus 4. And if you're happy using dimensional analysis, you will see that these two terms have the same dimension, so n is just a number, and this is a length to the n plus 2 on the bottom. Here we have a length squared over a length to the n plus 4. So overall, both of these terms have got dimensions of 1 over length to the n plus 2. And if we look at the other side, we have a length to the minus n, so 1 over length to the n. And every time you differentiate with respect to x, you will be reducing that dimension, so you would expect indeed to have dimensions of 1 over length to the n plus 2. So our result makes sense in terms of dimensions. Okay, so this is one of the three terms that are going to make up the Laplacian applied to r to the minus n. We've also got to work out this and this. But now what I'm saying is that we can just write those down by symmetry. If we had this differentiated with respect to y twice, this would be the same, and this would be the same, except here we'd have y squared. Similarly, if we're differentiating twice with respect to z, this would be the same, this would be the same, but here it would be z squared. So when we add all of these three terms together, we get that the Laplacian applied to r to the minus n is going to be this term 3 times, minus 3n over r to the n plus 2, plus, and then we get this structure multiplied by an x squared, plus a y squared, plus a z squared. This is r squared, so that partly cancels with this, and what we have therefore is minus 3n over r to the n plus 2, plus n times n plus 2, also over r to the n plus 2 when we simplify that. Putting these together gives us a common factor of n that we can take outside, and then we have plus 2 minus 3, and this gives us an n minus 1 factor. So we have n times n minus 1 when we simplify that all over r to the n plus 2, and that is our result. It's worth noticing that if n is 1, so we are applying the Laplacian to 1 over r, we would expect to get 0 because this would vanish in 3 dimensions. And if you'd like some more practice, why not just calculate this directly? Apply the Laplacian to 1 over r and see that it vanishes. Okay, with that, I'm going to move on to the next question. So on the second slide here, what I want to do is to apply the Laplacian to the sign of the scalar product of k and r and the scalar product of k and r is going to be k1 times x plus k2 times y plus k3 times z, where k1, k2 and k3 are the components of the vector k in the x, y and z directions. So the Laplacian of a scalar field, and this is a scalar field, is obtained by differentiating the field twice with respect to each of the Cartesian directions. This is it in 3 dimensions. So what we're going to have is the Laplacian acting on sine of k dot r gives us, so it's the second derivative with respect to x of the sine of the scalar product of k and r, plus, and then the second derivative with respect to y, plus the second derivative with respect to z. But I'm only going to write out this because I'm going to be able to write down the other terms very quickly by symmetry at the end. So the second derivative I obtained by differentiating this once and then twice. So let's just work out the first derivative here. The derivative of sine is cosine with the unchanged argument, and then we use the chain rule, so we multiply by the derivative with respect to x of the argument. We have the argument here, this is what we're differentiating, and the derivative on this is going to give us k1 plus 0 plus 0. So effectively all of this is a factor of k1, which I'm just going to put in front of the cosine. And then to work out the second derivative, we differentiate a second time, and when you differentiate cosine you get minus sine, and then repeating this structure again as we need to from the chain rule will give us another factor of k1, so we end up with minus k1 squared times the sine of k scalar product with r. Plus, of course, the other terms, but the other terms, I hope it's clear that by symmetry, when we differentiate twice with respect to y, we're going to get minus sine of the scalar product of k and r, but multiplied by k2 squared. And when we differentiate twice with respect to z, we're going to get this, but with minus k3 squared. So putting everything together, we get that the Laplacian acting on the sine of the scalar product of k and r is going to be minus k1 squared, sine of the scalar product, minus k2 squared, the same sign, minus k3 squared, the same sign. Pulling out the common factors of minus and sine of the scalar product of k and r, we have a factor of k1 squared plus k2 squared plus k3 squared, and that is k squared, the square of the magnitude of our vector k. And this is what we were asked to show. So with that, we'll move on to the final exercise. So in the final exercise, we want to show this identity. And again, we recall what the form of the Laplacian is, and I'm just going to do this in 2 dimensions, and I hope that when you do this it will be clear that it would extend to 3 or indeed any number of dimensions. So what we're going to do is we're going to take phi, differentiate it twice with respect to x, and then add phi differentiated twice with respect to y. But phi is going to be the product of 2 scalar fields u and v, and that means we're going to need to use the product rule. So the second derivative with respect to x is the derivative of the derivative, and when you differentiate u times v once, we're going to have du dx times v plus u times dv dx, and u and v are scalar fields in 2 dimensions, so these are partial derivatives. And then similarly, by symmetry, we're going to have this for the y derivatives. We now differentiate a second time, and when this derivative acts on this, it can either differentiate du dx, giving us a second derivative times v, or it can differentiate the v, and we're going to get plus du dx times dv dx. And then we have the derivative acting on this, and it can differentiate dv dx, giving us this term multiplied by u, or you can again get du dx times dv dx. So when this derivative acts here, we have du dx times dv dx. So there are two ways of getting this structure. And similarly here, if you work this out, you get this again with two ways of getting that structure. So now let's put similar terms together. This is the second derivative of u with respect to x times v, and over here we have the second derivative of u with respect to y times v. So let's put those two terms together. We have these terms which have a common factor of 2 that I can take outside, and then we have got this term, the second derivative of v with respect to x, and the second derivative of v with respect to y, both multiplied by u, so I'll put those together here. Now this is the two-dimensional Laplacian acting on u times v, and this is the two-dimensional Laplacian on v multiplied by u. So going back to what we're trying to prove, this is this term, and this is that term. We have a factor of 2 here, and now we look at this. So this is du dx times dv dx plus du dy times dv dy. Now the gradient of u is du dx I plus du dy j, and we would have exactly the same for the gradient of v, with v's here and here. And if we take the scalar product, we would have du dx times dv dx, so that the terms in the I direction multiplying together, and that's this, plus when we take the scalar product of the gradient of u, the gradient of v, we'd have du dy multiplied by dv dy. And that is this term here. So we recognize that these terms together are the scalar product of the gradient of u with the gradient of v. So we identify all of these terms as these, and that concludes our demonstration of this identity that I've called star here. So I hope that solving these exercises has been enjoyable and has helped your mastery of this topic.